In this module, we're talking about enthalpy, what it is and what we can do with it. So first of all, before we talk about enthalpy itself, let's look at some special conditions under which we can look at internal energy changes. First, constant volume. So if we're doing a chemical reaction or some process where the volume doesn't change, then first of all, we just write Q as having a subscript V. The subscript V means the volume's constant, and same thing with the change in internal energy. And so delta equals Q plus W, Q sub V delta E sub V. And W, remember, is negative P delta V. That's the only kind of work we're going to look at, so PV work. Remember that. So anyway, because W is negative P delta V, and when the volume is constant, what that means is delta V is 0. So this whole term goes away, and we are left with a really simple equation. Change in internal energy is equal to Q at constant volume. And what that means is if that a process occurs at constant volume, all we have to do to measure the change in internal energy is to measure the temperature, really, the change in temperature, because that's what we measure when we measure thermal energy is temperature, or that's how we measure thermal energy. Now let's look at what happens at constant pressure. So we call that Q sub P when the pressure is constant. So delta E is going to be equal to Q plus W, Q sub P delta E sub P, and remember W is negative P delta V. Now if we rearrange this just a little bit and solve for Q sub P, we got delta E sub P plus P delta V. Doesn't look like a big deal, but because most of the chemical reactions that we do in a chemistry laboratory do occur under constant pressure because they're open to the atmosphere, when we measure a temperature change, we're measuring Q sub P is what we're measuring. And so Q sub P is equal to not just the change in internal energy, but also the work term. So what we do is we define this new function that is a state function called enthalpy. The symbol is H, and enthalpy is defined as being internal energy plus pressure times volume. And the only way we define it like this, only reason we define it like that is, watch, because, okay, so this doesn't do us any good because we can't measure internal energy. It ends up we can't just measure enthalpy, but we can measure changes. So if we do a change in enthalpy is equal to change in internal energy, and at constant pressure plus the pressure times the change in volume. We pull the pressure out front of the delta sign because it's not changing if it's constant. But at constant pressure, delta E is equal to Q sub P plus W, and then there's a plus P delta V term again, and W is minus P delta V. The P delta V's cancel, and look at what we get. Delta H, the change in enthalpy for a process, is equal to the thermal energy transferred at constant pressure, which means that when a process occurs at constant pressure, when we measure the change in temperature, we're really measuring this function, which is the change in this function, which is enthalpy. It's a really useful function. And so when it's a chemical process. When a chemical process is what we're talking about, a chemical reaction rather is the process we're talking about, then the delta H for that reaction is called the heat of reaction. And if Q sub P is negative, that means that the system ends up at a lower energy, lower temperature than it started at. Thermal energy is given off. Delta H of reaction is less than 0, and we call that an exothermic process. On the other hand, if the thermal energy of the system is greater after the reaction occurs by absorbing energy from the surroundings, then delta H of reaction is greater than 0, it's positive, and we say that is an endothermic process. What's called a thermochemical reaction is just a normal chemical equation, but it includes delta H of reaction, thermochemical reaction, thermochemical equation. So, for example, the combustion of methane, that's what this is. This is an exothermic reaction because delta H is less than 0. This reaction here is an endothermic reaction because delta H is greater than 0, it's positive. Now, let's look at how we interpret our delta H of reactions here. Notice we don't put per mole here, just kilojoules, right? That's because, for instance, in this first reaction here, the yellow one, what this tells us is that for every 1 mole of methane, CH4, that reacts, we produce 802.4 kilojoules. But it also says per every 2 moles of oxygen that react, we produce this much energy. Or per every 1 mole of carbon dioxide that's produced, we get that much energy, or for every 2 moles of water that's produced. Down here, this says that for every 6 moles of water that react, we get this much energy, and so on and so forth. So let's look at an example here. We want to calculate what volume of methanol, this stuff's called methanol, is required to produce this much energy when we combust it. And I gave you the reaction, I don't expect you to know this yet, but this is the balanced chemical equation. And I also tell you the density of methanol, 0.7918 grams per mil. So we want to know what volume, how much methanol we have to burn to get this much energy. Well, from the thermochemical equation, we get, okay, so we want this many kilojoules. We know that 2 moles of methanol produce this much energy. Negative means it produces, and it's right here. And so this is just dimensional analysis from our chemical equation. Thermochemical equation 2 gives us that. Okay, there's our conversion factor. Kilojoules cancel. Let's do that. And we get moles of methanol. Now it's just normal dimensional analysis. That many moles, we need to know how many grams. The reason we need grams is because the density will get us from grams to milliliters, right? So if you take the moles times, this is the molar mass of methanol, we get the grams, about 3,230 grams. And then to get the volume, we just take the mass over the density, and we get about 4.08 times 10 to the third milliliters, or, because 1 liter is 1,000 milliliters, that's about 4.08 liters. And there you go.